So the next approach to regularization is very simple. It's known as early stopping. And so looking at this plot that we have here in blue, we are measuring the loss on the training set. In green, we are measuring loss on the validation set. And the pattern is pretty clear. So for training, you will usually see, unless your model is doing something funny, you will see that it will just keep going. The loss keeps going, getting lower and lower and lower until it's kind of bottoms up around some minimum value like 0. And validation error will, in most cases, it will initially go down. It will be also more erratic typically, and but you will in the regular case you will see that it will also at some point stop going down and possibly start going up. It will not go up as much as it started with, but it might increase. And so early stopping is the approach to regularization, or to you can also think about it as model selection. It's an approach which takes advantage of this pattern in the sense that we will save the model regularly. We save the current weights of the model, and we will keep training, and we will at some point once we run out of time for training, we will stop, and but we will not use the final weights. We will use the weights for which we find out that the validation loss is the lowest. So we will just choose the model, choose the weights at the point in time where we found that the validation loss was minimal. And so this is the kind of the crude approach, or the crude picture of this approach. In practice, there are some other things that maybe we are interested in measuring rather than just the loss. So the loss function is some function which quantifies the quality of the model in terms of like how much of an error it makes. But it's something that is typically easy to train or practical to use within our modeling architecture. It's not that doesn't necessarily exactly capture everything that we care about. So we might care about something, if we're doing classification, something like F1 score or accuracy at 10, or some metric which is not easy to optimize with backpropagation. And so we will typically, for the purposes of doing early stopping, we will be measuring that thing rather than simply the objective function, the loss function that we're training with. And so it is, since these two functions are not necessarily the same, so F1 score is not exactly the same as accuracy. It is also not necessarily the case that the model with the highest accuracy will also have the highest F1 score. So keep that in mind, that for the purposes of early stopping, we may be using another metric, because for early stopping we don't need the property that our function be easy to optimize via backpropagation. We will just measure it regularly after each epoch, or after some time has elapsed. We will record the value of this metric and continue training, and then choose the version of the weights with the best value of this metric of interest. So another approach to regularization that is often used especially in deep learning is called dataset augmentation, and that simply means that we generate or create some data, fake data. Fake in the sense that it was not part of the original training data, but so we manipulate the training data in a way which we think might reflect something about the variability that we want to capture. If we can do it automatically and generate some fake data, then we will just do it and add it to the training data, and then hope that our model is also going to learn to deal with such variations. So this technique is particularly effective and well proven for object recognition, because we know quite a lot about how object recognition works, which properties of images it depends and it does not depend, so it's invariant too, and so we can manipulate these properties. So these manipulations that I have listed here are translation, so moving an object from one place in the image to another. So if you're trying to recognize something, let's say that you're trying to recognize a face in an image, it doesn't typically matter whether it's slightly to the left or slightly to the right, or more up or more down. We're interested in just detecting the face, not exactly where that face is. So we can simply we can generate data which moves the objects in the training data in this way, while keeping the label the same. It should also be added that we can capture some of these things with the architecture. So convolutional neural networks to some extent capture already this particular property that recognizing an object in one place should work just as well as recognizing it in another place. Cropping is a similar thing. So we will, by cropping an image, so changing its size and which part we keep and which part we discard, we're basically also manipulating the location of the objects in that image, or maybe we're discarding some part of the object which may be not crucial necessarily. So again, going back to the example with faces, maybe we just have like the top of the head cropped off, so that should not prevent the system from recognizing that it's a face. We as humans, we would still recognize it a face even if there is, the top of the head is not present. Scaling is another transformation that is also something that normally a system should be able to deal with, or should be invariant to, in the sense that when we increase the image or decrease the image, it should not change the label of that image in the context of object recognition. Another property is rotation. So rotation is, as the name indicates, we just rotating the object in space. So if you have a face, if the face is inclined a little bit like this or a little bit like that, it should still be recognized as a face. And so rotation is a bit of a matter of degree. Maybe if the face is upside down, it's kind of becomes a bit more complicated for people to recognize it, and maybe also as a system we might not maybe want to recognize it just as well. So that depends on how exactly we want to deal with that. Rotation is less of an absolute of a manipulation which than the other ones that I mentioned, just because in the world that we normally see, there is the force of gravity, which forces a certain orientation on most objects. So people usually have their feet down and the heads up, and the same with other objects. And so this is something that is that shouldn't be be done to the same extent as translation or scaling. Flipping is a manipulation which basically creates a mirror image of an object. This again, in most cases, should not change the label of that object. Adding noise, some kind of noise to the object, we will typically, as humans, be able to detect objects even with substantial amount of some random noise or not even non-random noise in the image, and the same we would expect from our systems. And so these the manipulations that I mentioned are typically appropriate for the canonical cases of object recognition, but think about whether all of them are always appropriate and to what extent. And so while you're thinking, I'll give one example. So let's say that the objects that you want to recognize somehow are not invariant to flipping. So can you think of cases where creating a mirror image of an object will actually change its label? And so a typical example of such an object would be letters, right? Like the letters of the Latin alphabet, they are not invariant to flipping or to reflection in the mirror, right? The letter lowercase p, when we flip it, it becomes q, right? So if you're doing something like optical character recognition, we should not be doing this particular type of dataset augmentation. So in general, this is a technique which is widely applicable, but it's not always, it cannot always be done completely automatically in the sense that we will need to decide whether a particular manipulation is or is not relevant or appropriate for a particular use case. So how about other applications such as speech recognition? What type of manipulations would we do there? And so, of course, the nature of the data is quite different. And for this reason, also, the manipulations that we are doing are going to be of a different nature. But some of them are going to be similar. So the one that was shared with the case of images would be noise, and that could be, in the case of speech recognition, something like environmental noise, like people talking in the background, cars passing by, some other environmental noise from household appliances or any other noise that is not the speech that we're trying to recognize. Maybe the speech inherent in the channel and the microphone and so on. Similarly, random noise, we can just add random noise to our data, and also by that hope that the model becomes more robust to this kind of noise. We might want to mask maybe certain frequencies. So depending on what the channel is, sometimes when we're talking on the phone or on some poor quality microphone, maybe it just does not capture certain frequencies, like very high frequencies, for example, maybe not present. And we, nevertheless, even though we may find it a bit more difficult to recognize this speech, we still will be able most of the time to recognize it. And likewise, for a system, we would want it to be able to do that, even if some of the frequencies are missing. And similarly, if some short segments of the speech are missing, we should still be able to recognize it. So we can do this type of manipulation to our data to ensure that the model is taking that into account. One more thing, which is also pretty straightforward, is something like speed or pitch perturbation. So you might speed up the voices, the speech, or we might raise the pitch or lower the pitch. These are things that typically we can change without impacting too much our ability to understand what someone is saying. We can recognize, the speech of a small child or the speech of someone who has a very low voice, or someone who speaks very quickly or very slowly. And so likewise, we would want our speech recognition models to be able to do the same. And there are also some more specialized ways of data augmentation that are specifically designed for speech recognition. One of them is called vocal tract length perturbation, with the reference which I'm giving here. And that corresponds to manipulating the speech in a way which corresponds to manipulating something about the vocal tract, so our articulators. And if you're interested in the details, you can just consult this reference.